Hello everyone, we are computer science students from USN. My name is Tan Yijo and these are my teammates Shanghai, Afina, and Anis. In this video, we are going to talk about relation. The topic covers for relations are relations and their properties, representing relations, closure of relations, equivalence relations, and partial ordering.
In this video, we're going to see about relation topic. A set of ordered pairs AB such that A is from a set A and B is from a set B, where A is related to B by some relation. We can write as A or B. AB is element of R. A is related to B by R. Let's see some example. So we can see S is a set of students, M is a set of model phones, R is a relation which students use which phones. So as you can see in the following, R is the relation between S and M. Let's move to properties of relation, which are reflexive and irreflexive, symmetric, antisymmetric, and asymmetric, and also transitive. The first properties of relation is reflexive. A relation is reflexive if A is element of set A, therefore AA is element of R for all elements in set A. Below is the example of reflexive relation. The second property is irreflexive. A relation is reflexive if A is element of set A, therefore AA is not element of R for all elements in A. Below is the example of irreflexive relation. A relation is symmetric if AB is element of R, where A is element of A, B is element of A, therefore we have BA is element of R. And below is the example of the symmetric relation. A relation is antisymmetric if A is element of A, B is element of A. Whenever AB and BA are element of R, therefore we have A is equal to B. And the example for antisymmetric relation as below. A relation is asymmetric if A is element of A, B is element of A. Whenever AB is element of R, therefore BA is not element of R, or it can be said as both antisymmetric and irreflexive. The example as below. Let's move to the last properties of relation, which is transitive. A relation R on a set A is transitive if whenever AB is element of R, BC is element of R. Therefore, AC is also element of R for all ABC is element of A. Example 1. Is the relation transitive? The answer is no, because if we take 2, 1 and 1, 2, there is no 2, 2. For the example 2, is the relation transitive? The answer is yes, because all the elements meet the rule of the properties. Combining relation. A binary relation from set A to set B is a subset of a Cartesian product A times B. The relations are set, and combination use set operations such as union, intersection, and difference. Example, relation 1 and relation 2 is based on set A and set B. The operation used here is union. So, relation 1 union with relation 2 is as the following. Composite happen when there is two relations, such as R is a subset of A times B and S is a subset of B times C. So, the composite of R and S denoted as SR. SR consists of AC, where AB is element of R, BC is element of S, A is element of A, B is element of B, and C is element of C. Given two relations on set A. First, J is AB, where B is equal to 5 minus A, and second, K is AB, where A must be less than P. So, what is KJ? So, solution for KJ is AB, where B must be more than 5 minus A, or AB, where A plus B must be more than 5. Power relations are defined inductively by R power of 1 equal to R and R power of n plus 1 equals to R times R, or R power of n equals to R times R n times.
There is two ways to represent relations. First is 0-1 matrices, and the second one is directed graph or digraph. R is a relation from A to B. A is start from A1 until AM, and B is start from B1 to Bn. The matrix will be 1 if A and B belong to R, while the matrix will be 0 if A and B not belong to R. From A and B, so there should be 1, 1, 1, 2, 2, 1, 2, 2, 3, 1, and 3, 2. But 2, 1, 3, 1, and 3, 2 are belong to R according to the equation. So the rest is not belong to R. So 1, 1, 1, 2, 2, 2 will represent 0 while the rest is 1. So the question given two matrix and we need to find the join and the mid. Join means R. So it only requires at least half 1 between the two matrices and the result will become 1. For example, 1, 0 or 0, 1, then the result become 1. Next is mid. Mid is n is we need to both number to have 1, then only it will become 1. If one of the number is 0, then the number will become 0. Digraph. It consists of set V of vertices and with the edges A. Here E is represented by ordered pair of vertices. In the edge AB, A is initial vertex and B is terminal vertex. If H is AA, then this is regarded as loop. Let's take a look at this question. V have A, B, C, D, and the ordered pair will be AB, AD, BB, BD, CA, CB, and DB. So to draw the digraph, we will take a look at the ordered pair. So from the ordered pair, so A and B, A, the arrow will from A to B, A and D, so arrow from A to D, BB, there is a loop at the edge of the B, and the rest is just the same like A and B.
Closure of relation R with respect to property P is the relation obtained by adding the minimum number of ordered pairs to R to obtain property P. There are three types of closure relations: reflexive closure, symmetric closure, and transitive closure. The reflexive closure of R must be reflexive since R minimum relation that satisfies both conditions. For this example, we need to find the reflexive closure of R. To make it reflexive, add all missing diagonal elements. To obtain the digraph of reflexive closure, we add missing cell loops for all vertices. Second relation closure is the symmetric closure. The symmetric closure of R must be symmetric, contains R, and have the minimum relation to satisfy both conditions. For this example, we need to find the symmetric closure of R. To make it symmetric, we add all missing reverse elements. To obtain the digraph of the symmetric closure, R the opening function for each edge. The third relation closure is transitive closure. The R has the minimum relation that satisfies both conditions. For this example, we need to find the transitive closure of R. Since 1, 2, and 2, 3 is the subset of R, so we need to add 1, 3 to make R transitive. To obtain the diagram of the transitive closure, we add an arc from A to B if there is a path from A to B.
Equivalence relation is a set that is symmetric, reflexive, and transitive. Let us look at this question: x equal to y. Is it symmetric? Definitely yes, because x is equals to x and y is equals to y. Secondly, is it reflexive? The answer is yes, because if x is equals to y, y is definitely equals to x. Lastly, is it transitive? Yes, it is, because if x is equals to y and y is equals to z, then x is definitely equals to z. So, x and y is an equivalence relation as it is symmetric, reflexive, and transitive. Equals sign here creates equivalence class. Equivalence class is a subset of S which includes all elements that are equivalent to each other. The partition P of a set S is a collection of non-empty subsets of S such that every element of S is in exactly one of the subsets in P. Let us look at this example. S contains 3, 6, and 9. Is this a partition of S? The answer is yes, because it is a collection of non-empty subsets of S, and every element of S is in exactly one element of P. Is this a partition of set S? The answer is not, because it contains the empty set, as partition has to only contain non-empty subsets of S.
A relation R on a set A is called a partial order relation if it satisfies the following three properties, which is reflexive and is symmetric and transitive. For example, given a set A and set R, is R a partial ordering relation? Let's check. So firstly, is R reflexive? Yeah. All elements are diagonal in set A, which is 1, 1, 2, 2, 3, 3, and 4, 4. Is R antisymmetric? Yeah. By ignoring reflexive elements, there is no symmetric elements in set R. Is R transitive? Yeah, AB, BC, and AC are elements of A.
That's all for this video. Thank you.